and the function kind of looks like this actually. Okay, it looks like this. It looks like this. It never touches this line. So this is really the asymptotic line actually to the curve. Okay. In other words, I'm saying that the domain of the function is 0 to 1 excluded. Okay. 0, but 1 is excluded. Let's call 0 and let's call this point 1 actually. Then this function has an absolute minimum but not maximum. Okay. Doesn't have absolute minimum but not, what do you call, absolute maximum. Okay. So since we didn't have a closed interval, so we saw that if you don't have a closed interval, you can't have the maximum and the minimum both actually. Okay. Let's take another example. For example, I take now another function. Okay. Say for which, say this line is an asymptote. Okay. And the function which is, say for example, let's call it minus 1/2. This point is minus 1/2, and function goes like this. So it starts from some point here and goes asymptotically like this. So it never touches this line. So it goes with it. Okay. So again, your function is not, say, defined on, say it's defined on the interval. This function is defined on the interval -1 to say minus 1/2. Okay, but 1/2 is not included. So you can say it has a maximum but no minimum. Okay. So what does the extreme value theorem is telling you? The extreme value theorem is telling you, if you have a continuous function defined on a closed interval, then your function has a guaranteed maximum and a guaranteed minimum. If your function is not continuous, or it is defined or it is not defined on closed interval, then the both maximum and minimum are not guaranteed. So you might have a maximum but not minimum, you might have a minimum but not, what do you call, maximum actually. Okay, so this is what this beautiful simple theorem tells you. Now let's move to, what do you call, so all of this. Okay, maybe I must say one terminology. I must set one terminology. So if I say this is my function f of x, and this is the point C where the function has minimum value f of c. Okay. Then I'm going to use two terminologies. So terminology. Okay. So terminology. So I'm going to say that I'm going to read it as that at x equal to c, maximum occurs. So the input where our maximum occurs are, I'm going to say x, or the f of x has a maximum at c, at x equal to c. So if this is the situation, I'm going to say at x equal to c, maximum of the function occurs. In other words, function takes its maximum value, and I'm going to say that at f of x, the function has a maximum at x equal to c. Okay, so these are the both terminology I'm going to say. So the inputs, for inputs, where you have maximum and minimum, you're going to say that at x equal to c maximum or minimum occurs, or you're going to say at r f of x has a maximum or minimum at x equal to c. While this value f of c is maximum value, okay, we're going to call this as maximum value. Okay, so c, the point where maximum occurs, okay, a maximum of the function occurs, and f of c, the maximum value of the function actually. So c is the input where maximum occurs, and f of c is the maximum value, the maximum output that you had actually. And similarly for what you call the minimum. Okay, because sometimes you will read actually that, okay, we say that the function has maximum at x equal to 2. Okay, the function has maximum at x equal to 2. It doesn't mean that x equal to 2 is maximum. It means that x is equal to 2 is the input which gives you the maximum output value. Okay, x equal to 2 is the input that gives you the maximum output value, or x equal to 2 is the input where you get f of x gets the minimum value actually. Alright. So what is the summary of the discussion so far? So what is absolute maximum? What is absolute maximum? Biggest of all, the value of the function that is bigger than all other values in the given domain. We call it absolute maximum or the global maximum. And what is absolute minimum? The value that is smallest of all values in the given domain. What is local maximum? Local maximum is the maximum which is valid for interval, okay, sub-interval, not for entire domain. What is local minimum? Local minimum is the minimum which is valid for, which is the minimum for a small interval, not for all values. Then a function can have multiple maximums, one maximum, no minimum, no maximum, one minimum, one maximum, one minimum. So it can have two maximums, one minimum, so on and so forth. It can have infinite maximums and infinite minimums. It can have no maximum and no minimum, and so on and so forth. And then finally we said that we have this beautiful theorem, extreme value theorem, which tells you that if you have a continuous curve, if you draw a continuous line segment, okay, or if you have a continuous curve or a continuous function but defined on a closed interval, then that function must have an absolute maximum and absolute minimum. And if your function is not continuous, then it's not necessary that it should have maximum or minimum, or maybe it doesn't have anything. Okay? Or if your function is continuous but not defined on closed interval, still that function is not going to have both maximum and minimum. So this is what the summary of the discussion is. So you have to read the book actually. Okay, you have to watch this again. Just draw the scribbles and just draw the scribbles and think about these things for the first time and make sure you understand them actually. Okay. So we understood so far the nature of maximums. So if I write a one-liner summary of what we did, so we have answered the question. You should be able to answer the question after this discussion. What are maximum and minimums? Okay, maximums and minimums. How many max and minimums a function can have. So we should have a clear picture of this. Function can have. So it can have no max, no minimum, one max, one minimum, and so on and so forth. Infinite max, infinite minimum, so on and so forth. A function can have how many function minimum function can have, and when the function is guaranteed to have max, absolute max and absolute minimum actually. Okay? So we have kind of tried to make sense of these three things. Okay? What are maximum minimums of a given function? How many max and minimums? How many max a minimum function can have, and when a function is guaranteed to have maximum and minimums. Now we are starting the discussion to the next topic. Given a function, how to find maximums and minimums? How to find max and minimum. Okay, so the next task is, so we know about the nature of it, now let's try to, what do you call, find maximums and minimums. Let me draw a curve and ask a question from you. Imagine I have a curve like this actually. Imagine a curve like this. I know this function has a maximum and a minimum. So the maximum occurs at this point and this is maximum value, and the minimum occurs at this point and say this is minimum value for this function. I would like to ask one thing from you. Can you guess what is the common between these 2 points? There is something interesting happening at these 2 points actually, which is common in both. So pause the video for a minute or a second and think about what is so special happening at this point and this point actually. What is so special happening at these 2 points? Why this point is maximum and this is minimum? Why these are 2 special points? So pause the video for a second and think about it. If you have thought about it, one thing that is common in both is that, think about it, that curve was increasing first, and after that part the curve started decreasing actually. So you went up and then went down, so therefore this is maximum. And how about this point? The curve decreased first, the curve was decreasing before this point, and after this point the curve is increasing. Let's draw a tangent line at this maximum point. Okay? Let's draw the tangent line at this maximum point. Let's call these the coordinates of points as C and F of C. Okay, so let's call these coordinates as C and F of C. And let me ask from you, what is the slope of this tangent line at maximum? This line is parallel to x equal to 0. If you try to find the slope of this line, can you think of it? What would be the slope of this line? You're going to say the slope of this line is obviously f prime of c, but this slope is 0. There is no slope actually here. Okay? So the maximum point is a point where the slope is 0. How about minimum point? Try to draw, for example, a tangent line at minimum point. So what happens? So you can see that again this line is a horizontal line. So therefore, if at a minimum point you draw a horizontal line or a tangent line, that tangent line has a slope 0. So let's call this point as D and say f of D. So f prime at D is also what you call 0. So if you have an extreme point, a maximum point, draw the tangent line at that point, the derivative is 0. Draw the tangent line at a minimum point. What is the slope of this tangent line? Tangent line at the minimum point, the slope is 0. In other words, the derivative is 0. So I can put this information by observation based, and no matter what maximum, no matter what curve you have, you're always going to have it actually. So this is maximum, so draw a tangent line here. You're going to say that this is this has a slope 0 and this is minimum line. So draw a tangent here and the tangent has a slope 0. Okay. So let me put this information, so this interesting information in the form of a theorem actually. What is the theorem? This theorem is called the Fermat theorem. This theorem is called the Fermat theorem, and it says observe interesting thing. For a given function, okay, if x equal to c is a maximum or minimum, x equal to c is maximum or minimum, and this maximum is true for both local and absolute, both kind of maximums. Maximum or minimum. So if you okay, so given a function f of x, if at x equal to c, if at x equal to c, or if, just like if x equal to c is the maximum local or absolute, or minimum local or absolute, then the derivative, the slope of the tangent line at that maximum or minimum point must be 0. Must be 0. Okay? Must be 0. So this is what we call the Fermat's theorem. So what says Fermat's theorem? If your point at which you have maximum or minimum, you know already that it is a maximum or minimum, then at those points the slope of the tangent line, in other words the derivative of the function at point C, maximum or minimum, must be 0. Must be 0. It must be 0. Okay? Let me put a definition. You call such point where, so for a given function, for a given function f of x, if f prime of c is 0, at some point x equal to c, then you call such point as critical point. So there are different names for it. Critical point. Why it's critical? Because after that, before that point and after that point, the function changes its behavior actually. Before that it was, in decreasing, and after that it is increasing actually. So increasing, and before increasing and after decreasing, so that must be, what do you call a critical point. So critical means something is changing its behavior, turning into something different actually. So it's called critical point. Some people like to call it turning points. Okay? And it's true. The curve is turning at this point. So before that, increasing, and after that, decreasing. Before that, decreasing, and after that, increasing. So it's turning point. Some people call it stationary points actually. So there are different names for it. Stationary points of f of x. Should be truly called a stationary because the curve has stopped changing at this point. So it has kind of stayed and then moved to the, what do you call, the opposite behavior actually. So increasing, stopped, decrease. Decreasing, stopped, increase actually. Okay. So you call, these are the different names that you give to basically such function. Now, maximum, so what follows from this definition? Maximum is a critical point and minimum is also a critical point. So any point where the derivative of the function is 0, you call that as the critical point actually. So what is critical point? Where the function has derivative equal to 0, because that derivative basically represents the slope of the tangent line. Okay, and that slope becomes 0 because the line becomes parallel to x-axis actually. Alright, and have another look at Fermat's theorem. What does the Fermat's theorem says? That if you know in advance that x equal to c is a maximum or a minimum, then at that point the derivative of the function should be 0. In other words, that point should be a critical point actually. That point should be a turning point. So in other words, maximum and minimum are critical points. Maximum and minimum must be a critical point actually. But here is the interesting thing. So I hope you are doing logic, that every if-then statement has a converse actually. Converse of this statement is not true. What do I mean by that? If a point is a critical point, it is not necessary that it should be maximum or minimum. Okay? If a point is a critical point, if a point is a point where the derivative of the function is 0, okay, it is not necessary that the function should have a maximum or a minimum at, what do you call, that point. Okay, so therefore the converse of the Fermat's theorem is not true. If your function has a maximum and minimum, that point should be critical point. The maximum and minimum should be critical point. But if there is a critical point, it is not necessary that it should be maximum. So here are two examples, two very interesting examples actually. So consider this curve. Consider the graph of f of x equal to x cubed. So it goes like that and goes this way. Okay. If you wish, you can have this and this actually. I know about this function, so this let's assume that this is a graph of f of x equal to x cubed, so it's a graph of f of x equal to x cubed. This function, if you take the domain of this entire R, has no maximum and no minimum, because there is always a smaller value than the value that you have, and there is always a bigger value than the value that you choose. So this goes on forever actually. Okay? So this goes on forever. Can you think of having a critical point actually in this curve? So where is a critical point? In other words, where is the point where you draw, if you draw the tangent line, that tangent line has a slope 0? Or where is the point where the function has a 0 derivative? So you're going to say, this is the point, if you draw the tangent line, that tangent line has a slope 0. Okay? So I'm going to say that x equal to 0 is a critical point. If you try to draw a tangent line, the tangent line would look like this. Okay? And this tangent line has a 0. So x equal to 0 is a critical point. You can also see that if I, for example, differentiate f of x equal to x cubed, 3x squared, and I substitute say f prime of 0, okay, and I substitute say x equal to 0, I'm going to get 0. Okay, so f prime of 0 is 0, so therefore x equal to 0 is a critical point. But this critical point is neither maximum nor minimum. Why? Because before that point, function was increasing, and after this point, function is still increasing. So function is not changing its behavior actually. It's not like this, that before that it was increasing and after that it was decreasing, and before that it was decreasing and after that it is increasing. So it is not like that actually. Okay, so the function does not have. So this point is a critical point, you can call it, but this is neither a maximum nor a minimum. Okay, because the function is not changing its behavior, you know, what do you call, before and after that point. Before it is increasing and after that it is also increasing. So you call such critical point, but not neither max nor minimum. Okay? In other words, a point f prime of c equal to 0. Okay? You call such point as the point of inflection actually. So the name that you give, so x equal to 0, is the point. So you call it the point of inflection. Okay? So you call such point as the point of inflection. Okay. So another example could be that if you draw, for example, another curve. So consider this curve that goes like this. So this also has, what do you call, a critical point. Okay, a critical point. So you're going to call such point also as the inflection point. X equal to 0 is also inflection point, because before that the function was decreasing and after that function is still decreasing. The function is not changing its behavior. Okay, it's going down and after that it is going down. So what is the summary? The summary is that if you compute, for example, derivative of a point and it turns out at a point f prime of c is 0. Okay? F prime of c is 0. Then there are three possibilities for c. In x equal to c ke liye, there are three possibilities. It could be a maximum. It could be a minimum. In other words, it could be a point where the function is changing its behavior. It could be a point where the function is changing its behavior. So it could be a maximum, it could be a minimum,